copy. Okay, so thank you everybody for attending here. I realize the COVID-19 world isn't ideal for defenses, and I do appreciate everyone coming in to a virtual presentation here, and so thank you. And so today we're here to experience Steve's dissertation defense. And so I'll share my screen here. And just to give you a little background about Steve, in the last several years at University of South Alabama, Dolphin Island Sea Lab, Steve has been a busy body and particularly productive given some of his circumstances that he's had to deal with. In addition to COVID-19, Steve has had a number of other hardships that he's been dealing with. And so the fact that he has been able to get out when he has is a real tribute to his work ethic and his ability to get things done under unusual circumstances. And so just to give you a little description about Steve and some of his work, I have a number of accomplishments here, but I know many folks at the Sea Lab do a lot of fisheries work, and we too in the DZ lab do fisheries work. It's just a slightly different kind. As you can see here, there's a picture of Steve fishing out a drifter from the ocean, right? So we do a sort of fishing, not quite what we typically think about, and maybe not as exciting as picking up a big red snapper, but we do our sort of fishing. But outside of our sort of field work, Steve has been pretty busy. He has one first author publication out in water resources research. He has another paper submitted there that we should be hearing about any day now. It's with the editor for decision, so we should be hearing back on that very shortly. And then he has another paper in prep that'll probably go to something like GR, a top tier journal that we're still sort of figuring out. In addition to those first author works, he's also been extremely busy on various contributing projects that sort of we've been doing in my lab, where he's a co-author on 6 other papers. And he has another co-authored paper that he is in submission, and he has several other contributing efforts in prep. So he has been very good at getting out and working with other people. And as a result of that, he's got a lot of co-authored publications. He's also been busy trying to bring in money for himself as a graduate student. He has wrote a number of award and fellowship applications, and to his credit, he has failed in some cases, but has succeeded in quite a few, where he's got a number of travel awards, and importantly, he also got an FDA DISL fellowship, and so that's been very good for the last, I guess, year and a half or so, maybe 2 years, I guess now. And so he has been active in grant writing and in particularly with fellowship applications and award applications. But he's actually recently submitted something with some colleagues recently that he's done a lot of the lion's share of writing. So he's really into writing as well now, or at least grantmanship. So he's making an effort on that front as well. And he's also been very vocal in getting people to know what he's doing. He's had a number of local and national presentations. He's got 18 plus scientific presentations, a mixture of poster and oral presentations. A particular highlight would be he got best presentation at the Young Coastal Scientists and Engineers Conference. And as you would imagine from all this work, he's participated in a number of things, right? He's contributed to a number of research campaigns. A lot of them were associated with Gomery, both Concord and Carthy. He sort of had some experience with. He's also done some local things. He helped me out with some water quality work in Banks Lake way back when he first got here. And so he's been pretty active getting his fingers in different things. He's also participated in a number of different outreach efforts. He's done Discovery Day, boardwalk talks, a number of other things where he's interacted with the public, telling them about his research. And so this is all to say he's been very busy, and he's got a nice slate of work that he's accomplished for his PhD, and I'm excited for him to tell you guys about it. And so with that, Steve, I will turn it over to you.
Thanks, Brian. share my screen. All right. Well, we'd like to thank everyone for joining. So I'm excited to share my PhD defense here on the role of river discharge on flooding and tidal dynamics in the fluvial-marine transition. I'd like to begin with a few acknowledgements and thank my PhD advisor, Dr. Brian Zonkowski, for his support in this work and continued encouragement. Also, thank you to my committee members, Kelly Dorgan, Brett Webb, and Arnaldo Valle-Levinson. This work has been funded through the Dauphin Island Sea Lab Food and Drug Administration Fellowship. And with that, we'd like to thank my FDA mentor, Kevin Kelsey. Funding earlier on was from the Concord Consortium, which is part of the Gulf of Mexico Research Initiative. This work would not be possible without the Lord as my light and my salvation. And so I'm grateful for his guidance in this, as well as just motivation for my overall work to steward this world. Thank you to my family for your patience and support, both my wife and kids and extended family. In addition, my church community and the Dauphin Island Sea Lab community as well. I'd like to begin broadly thinking about the Earth's surface, which is composed of the land and the sea. And what we generally think about these interacting often right at the beach in the shoreline, which is where we actually find ourselves today at the Dauphin Island Sea Lab. But when we think about the processes, though, that actually connect the land to the sea, it's often done in global models by coupling land models and sea models. And the major conduit that we end up seeing in these models and in the overall processes is that the rivers provide this primary conduit to connect, whether we look at the water cycle or the rock processes from source to sink, or the carbon cycle. Rivers play the dominant role transporting the terrestrial processes and material to the sea. Along this transition from rivers to the sea, we find that most of our megacities and our ports, this concentrates human populations, infrastructure, and overall economies in these transitional areas. They're also valuable as fisheries and are places where we generally enjoy getting out to, enjoying the natural habitats and the recreational purposes that they have. But along these transitions, we also have a lot of problems and challenges, often coming from outside as allogeneic processes, things such as flooding, erosion and subsidence, water quality issues, and sea level rise and salt intrusion that can be seen changing today, these environments. So today I would like to begin with a general introduction to the fluvial-marine transition, share some of my methods, look at the study region, and then dive into 3 studies I've done, be generally summarizing them, and then end with a short closing. So to introduce the fluvial-marine transition, this is essentially a bridge between the land and the sea. So from the marine side, we often will see tides and even storm surge transporting the energy landward, or even salt water, as density gradients can also be a part of this. Or from the fluvial side, from land, the rivers and fresh water are moving seaward. When we think of the geometry of the system, or the geometry of the oceans, They cover the Earth and then are relatively shallow. Thus, the dominant geometry is horizontal as they are wide. And with rivers, they flow downstream. Thus, the dominant geometry there is vertical. So looking a little bit more at the overall geometry, from the marine end, water or tides may first move into a wide bay that then becomes narrower in a landward direction. And then river flows come from the inland areas moving seaward. The river energy decays then in a seaward direction, and the tidal energy decays in a landward direction, sometimes peaking through a constricted region near an inlet, but through the width convergent area, the convergence ends up balancing the friction, and the tidal energy or the tidal amplitude remains fairly consistent. Then as we get further inland, there's less convergence, and the river energy or the river flows are stronger. And this causes the tides to begin to attenuate. And as they attenuate at an inland point, the tides cease to exist. We can call this the tidal limit. And then where the tidal energy or the tidal discharge balances the river energy or river discharge, we have the flood limit. So here, we can delineate the area where we have bidirectional flow with floods and ebbs. But then at this point of the flood limit, the flood tides are no longer strong enough to reverse the river flows. And so the tides then just simply modulate the unidirectional flowing rivers. So in this unidirectional flow area, we can refer to this then as the tidal river, where flow, you can think of it more as being pulsing, fast, slow, instead of reversing, which we have in the estuary region. Now, often we end up forgetting about the vertical component of these systems. So now looking at the vertical, there may be some tidal scouring here near the inlet, but in general, the area where we may have a bay or is width convergent is usually fairly flat. And the most dominant feature is usually a deep hole region that occurs from the river scour during high discharge. So that during most conditions, the water surface slope ends up diverging from the bed. And this causes the water to slow down, and we can call this then the backwater region. From the tidal perspective, which are moving landward, this then creates another convergent area where we have a height convergent section. Thus, we have a height convergent region, usually in the inland areas, and a width convergent area in the seaward regions. So because most of us in this community are more familiar with marine processes, let me just introduce to you briefly river flood waves. These waves occur because of precipitation events that occur inland, raising the water levels locally, and then later the water levels rise further downstream. Thus, it can be observed as a wave. To look more closely at this, we can look at a fluvial-marine transition here, where we have 4 stations that are color-coded there with the dots, and look at this in terms of a precipitation event. So this event here of the precipitation is captured on the y-axis on the left, and is shown with the blue bar graph here. So we have one large precipitation event that's occurring, and then the water levels align with the right axis, and are color-coded to the stations. And the most inland water levels then peak a few days after the precipitation event. And we can see this as a lag time between the precipitation to discharge. And then the peak water levels occur at a later time, and thus we have a seaward propagating river or fluvial wave in the system. These waves and this lag time can be important when we have events that can affect both the sea and the land, such as hurricanes. So I know many of us have been affected by hurricanes, even recently from Hurricane Sally, which I have shown here, where it brought strong wind and precipitation. This event did a lot of damage to the Dauphin Island Sea Lab. Even the winds brought a surge flood that moved in a landward direction, and the precipitation brought a river flood that moved seaward. And so when they overlapped in the same space at the same time, this created a compound flood. And so the compounding raised the water levels more than just simply one of the two events, and for a longer period of time. So as many people then are interested in the land-to-sea processes or even the transition, there's a few different approaches that we may take in trying to understand this region. One is just simply to have no transition. This might be a source to sink type of approach, or we could call this next one a black box, whereby in the transition, there's maybe some sort of tuning parameter that we use, or maybe a fraction of sediment deposits or something. But most of us who work in this transitional region have our focused areas, whether we're on the shelf and there's regions of freshwater influence, or maybe in a salt estuary, or even exchange in between the two. Or we could be on the flip side of this and be a fluvial hydrologist, where we work much further inland, where river discharge can be accurately measured, but don't venture down into these backwater regions where marine forces can be present. So this ends up creating a large region of uncertainty in between. This can sometimes be 2 to 3 times as long as the salt estuary itself, and is often dominated by freshwater tidal dynamics. So, so really one of the major underlying motivations for this work is simply to understand, how do we bridge the entire gap between the rivers and the sea? So for this, I decided to focus in on a few different pressing issues in my dissertation. One is linking the atmosphere and watershed to the fluvial-marine transition. The second is looking at the river dynamics themselves along the transition, and then how the river affects the marine processes and even the geomorphology along this, transitional environment. And so to do this work, I have worked with a variety of long-term observations, predominantly water level and velocity. And the primary analysis that I've done is with time series, and have incorporated, in addition, wave theory analytical solutions and statistics. You can see here the NOAA station at Dauphin Island. This is one of my longest water level stations that I've used. So thank you, NOAA. The study region itself, where I've applied these methods, is in the Northern Gulf. in this area, the watersheds have a high annual precipitation. This precipitation is relatively spatially consistent. And the watersheds then of interest are the Pascagoula, which is the largest freshwater source to Mississippi Sound, and is the largest undammed watershed in the continental US. Then the Tombigbee, Alabama watershed flows into Mobile Bay and is the 4th largest discharge in the continental US. And then the Apalachicola flows into Apalachicola Bay. From the marine side of things in the Gulf of Mexico, as tides enter into the Gulf, they find themselves in a basin that is resident for diurnal waves. This causes the diurnal waves to be larger and the semi-diurnal waves to be smaller. This then creates a diurnal microtidal environment that has relatively low energy in the tides. This can be contrasted with the large seasonal hurricanes that come through and are very high energy. Thus, we have a bimodal energy environment. Now, if we want to focus in on where the diurnal tides, or I should say where the tides are most strongly diurnal, this is calculated using a form factor. We can then capture Mobile Bay and look at the fluvial-marine transition here. This fluvial-marine transition begins on the Tombigbee and the Alabama rivers, up at the dams that function as weirs during high flows. But during low flow, tides can reach all the way up to these dams. And then the water itself, as it flows downstream, it comes into a large delta. Here, the Tombigbee, Alabama Delta is about 2,000 square kilometers. And then water flows into Mobile Bay, which is about 1,000 square kilometers, and then out through Main Pass to the Gulf of Mexico. Some water moves through Mississippi Sound to the Gulf. Now, if we focus in a bit more on the Delta region, particularly from the confluence of the Tombigbee and Alabama, here in the middle Delta, they flow together for about 10 kilometers. And then we have our largest bifurcation, where we have a distributary called the Mobile River and the Tensaw. The Tensaw is fairly anapomosing, and they remain separate as separate distributaries down to Mobile Bay. The upper Delta region has much higher relief. As you can see, a lot more brown here, and this then outlines the Alabama River here with large levees, compared to the lower Delta, which has less relief, apart from the city of Mobile and the port itself, right there at the head of the bay. So now we can look a bit closer at the first chapter, looking particularly at the role of precipitation intensification. This precipitation intensification occurs now due to global warming. So as the atmosphere is warming, more water vapor can be held within the atmosphere. More water vapor then in a given precipitation event increases the volume of precipitation. So this precipitation intensification, as it falls on the earth, it saturates the soil, and we have more runoff. This runoff moves faster downstream, or faster to the streams and downstream. And recent work in the central United States shows that global warming is increasing the frequency of river flooding. And so this has been done in inland regions, but I'm particularly interested to know if precipitation intensification is affecting the fluvial-marine transition, and if so, how. So the hypothesis for this work is that precipitation intensification is increasing the frequency and the frequency of coastal river flooding and compound river surge events. We can then look at the discharge itself from our three watersheds to try and identify if this is occurring. So we find ourselves here with three hydrographs from each of the watersheds, capturing 90 years along the x-axis and discharge on the y-axis. There's quite a bit of annual variability in each system, but to better capture the variability, we can just focus in on the Tom Bigby, Alabama here, and we can take a wavelet analysis of this. Don't worry if you're not familiar with the wavelets. Let me just kind of walk you through this briefly. So on this color plot here, we again have the x-axis capturing our 90 years, and on the y-axis we have the period. So if there's a strong signal at a given time of a given period, we have a bright color there. So a constant bright period over time, captured with a horizontal bar here, is the annual trend. And this remains fairly constant. Well, I should also note the outlines here capture these significant areas. The vertical the vertical bars here capture events that happen at one time and span multiple periods. So over time, when looking at these events, we see that we transition from low frequency events to higher frequency events. Now, if we want to quantify this a little bit further, we can take a mean of the first 30 years and the last 30 years at each period. This is also referred to as the global wavelet spectrum. So the mean here for each of these 30 years captures a strong annual signal, and there's a fair amount of high energy or higher frequency as well that's captured. Then looking at the change over time, we see that the lower frequency has actually decreased and the higher frequency has increased. Thus, we have a shift towards these higher frequency events that's there. Now, to capture exactly when this occurred, we can take a change point analysis of these significant events using a Petit test for each period. And so that's where we have each one of these dots. And so the dots represent when there was a significant change at each period, and generally see that it occurs for these higher frequency events and cluster around 1970. So we clearly can see that there's a change in frequency, but to further analyze these discharge events in a more traditional hydrology approach, I also used generalized Pareto distributions and found that for all the watersheds within the tidal reaches, the river flood frequency doubled between the first 30 years and the last 30 years that we see there. So this may beg the question, what is causing this? So in looking for the answer to that, I looked at the precipitation volume, the discharge volume, the runoff ratio, land cover, just to name a few. And none of them actually explained the the change in flood frequency. But I did find a significant change in the precipitation discharge lag time. So to demonstrate this, I have the lag time for each watershed for each year with a dot. And we have this over our 90-year period. Then before and after these significant changes in each watershed, I have a bar capturing the mean. And so we see that over time, there's a significant decrease in the lag time between precipitation and discharge at the coast. The precipitation events also significantly changed, capturing the precipitation events at the 82nd quantile for each year. I have them displayed in the same way. And we see that there is a significant increase in the precipitation events. These significant changes in the event precipitation and the lag time both were approximately at the same time in each watershed. So we see this connection between the precipitation intensification and a shorter discharge lag time causing this increase in flooding. But now, how does this actually interact with the marine events themselves that are happening there? So we can do this by looking at at a couple of different hurricanes. The largest hurricanes that we've had in recent history are Hurricane Katrina and Rita, and these ones were both about a month apart, and they brought very high precipitation. So these two figures are laid out the same way as the figure I showed earlier. So the large precipitation event from Katrina is captured here, and it coincides with a large rise in water level at the coast. A little bit later, the water levels rose peaked further inland. And thus we have then a landward propagating surge wave. A few days after this large precipitation event and the surge beginning at the coast, we had peak water levels inland. And then these peak water levels then occurred at a later time further seaward. And so we have a lag time then and a seaward propagating river or fluvial wave across the system. Now, where this river wave and the surge wave overlap in the same space at the same time, we have compounding. And so compounding is not just simply occurring at this one space, but we see it occurring in multiple stations for both of these events. So we see then that there's a temporal aspect to this, whereby reducing the lag time within the system, this then increases the likelihood of the compound events. The spatial component that's here is also important in that the lag time caused the compounding to occur at the inlandmost stations. And this can be contrasted then with really no compounding being observed directly at the coast, which we may expect, and where that is often sought for in a lot of current research. Thus, they would then miss the inland compounding. But I would also like to point out that in looking at all of the compounding events that we have data for here, generally the compounding events did not cause the largest floods, because the largest floods themselves were caused by rivers, and the rivers were delayed, the largest river floods were delayed inland, thus having a much longer lag time, and so there was not compounding then that occurred. So if we summarize these results, we can look at, in the atmosphere, we had precipitation intensification. In the watershed, we had a shorter lag time. Then in the coastal environment, this increased the flooding frequency and the magnitude of the river floods. This also increased the likelihood of compound river surge events. The compounding itself had temporal and spatial variability, and generally the compounding occurred far inland near the tidal limit and not directly at the coast. And lastly here, in the fluvial-marine transition, the flooding solely from rivers posed the greatest risk. So, need a sip of water there, a coffee. As these river events then play a critical role in the fluvial-marine transition, we can look at the dynamics of the river waves in the fluvial-marine transition itself. I will generally summarize this as I've shared these findings with most of the community here, but I'll note here at the beginning that there's generally an assumption in hydrology that these river waves in the fluvial-marine transition are complex, but they quickly attenuate, and so they're really beyond the scope of interest for the hydrology community. And from the oceanography perspective, the river waves are viewed as being much longer than the fluvial-marine transition, and therefore there's really not any temporal or spatial variability, and they don't really matter. We can basically take the inland discharge and just apply it downstream at the coast. But I wanted to actually test that and to see if the river events do propagate through the fluvial-marine transition. And the hypothesis for this work is that river waves do propagate through the fluvial-marine transitions where the geometry and the marine forces affect the wave momentum, making them temporally and spatially variable. In a traditional river environment, as the events are larger, the lag time usually decreases. In the fluvial-marine transition, I found that it deviates from this trend, and actually the largest events can be the slowest events. And then looking at the magnitude of the events, comparing an upstream measurement to a downstream measurement of discharge, there's usually close to a linear relationship in a traditional river environment. Well, in the fluvial-marine transition, it actually diverges. And so we have less water generally flowing through compared to the upstream measurements for the different events, particularly as they become larger. Well, looking closer at this, I found that when the river flow is confined to the channels, it generally followed a traditional assumption from hydrology. But due to the fluvial-marine transition broadening out and becoming much wider due to the marine influence, I found that the wide floodplain made a big difference. So in these reaches, the levees often become larger and they constrict the river flow. But as the water levels rise, they don't have to completely submerge the levees in order for flow to go through gaps or crevasses through the levees. And because the floodplains are larger than traditionally are observed inland, we have a lot more water that is lost and that goes into these floodplains. Then at even higher discharges, where the levees do become submerged, friction becomes even more important for the system. This can be due in part to the vegetation that can increase the friction, but this also increases the pressure gradient, and then we have an increase in flow over the floodplains. Thus, there's a small increase then in the magnitude here that I show. So these thresholds that we see due to changes in the fluvial-marine transition seaward of where discharge is usually observed explain some of the critical changes of estuarine and shelf environments, particularly estuarine flushing and even water quality. And then on the shelf, it also explains the change in the size of the plume itself. So these effects along the fluvial-marine transition can change shelf dynamics as well. If you're interested in checking out more on this first work on this first work analyzing river wave dynamics in the fluvial-marine transition, you can check out this published paper with Brian. Because the river dynamics are important to the marine environment, or to the fluvial-marine transition, we also want to look at how they affect the tide and the geometry of the system, which is the third chapter here. And so, multiple works now have identified that river flows do affect tidal dynamics, but sometimes river flows can cause tides to become larger or tides to become smaller. So there's some uncertainty exactly where this occurs, and then also there's also a bit of uncertainty as to exactly where do some of these changes occur. And so for this, I'm particularly interested in understanding as we change our river flows, how does this translate then to the spatial location along the fluvial-marine transition of the river and tidal dynamics themselves. Looking here briefly at the river discharge from the year 2010, we see some large flow events and some low flow events here, or sorry, some period of low flows. Then we can look at the water levels across the transition for the same area, or for the fluvial-marine transition. These colors coordinate with the colors of the line, and then are spaced out by 1 unit. The same is true for the velocity observations also, and the colors coordinate between these two. So we generally see that during this low flow period, all the way inland near the dam, we have fortnight variability capturing the tides. In fact, at these dams, 238 kilometers inland, the tidal amplitudes during really low flows are about the same as at Main Pass at the mouth. This is in part due to the tidal reflection off the dams. Now, when we have higher flow conditions, we see that the tides basically disappear in these inland reaches, and the variability is driven by these river events that are occurring. And then in the velocity observations, we see similar trends, and where the high flow then causes the rivers to no longer reverse in the system. So to really pick apart these tide river dynamics, we have to look at changes in the geometry as this can affect the tidal dynamics. So I'll just summarize this for you. Analysis of the area shows that there's no significant cross-sectional area at the bayhead. This may be surprising as there is a large width to depth ratio change, but not a significant change in area here. The largest change in area actually occurs closer to the middle delta, kind of middle lower delta, where there's a significant change in the height, the width, and the sinuosity of the system. More specifically, on the Mobile River, this occurs near the I-65 bridge, and in the Tensaw, it occurs near the bifurcation with the Middle River, which is a local avulsion here in the system. And there was not a significant change actually overall at the Mobile Tensaw bifurcation. So this then overall creates a width convergent area for the tides as they propagate landward that has a similar width convergence for the bay as it does for the lower delta. And then in the middle delta landward to the dams, we have a height convergent area that's a backwater. This height convergent area is a little bit weaker than the width convergent that we have. Now, to try to summarize the tide river dynamics along this transition, we can look at the observations from all the stations that we have. And I'm putting it here on the y-axis with the distance inland, or I should say the distance inland is on the y-axis here, roughly corresponding to the map, just to the left here. So we have the bay, the delta region, and then landward of the delta apex. So the geometry change roughly occurs here in this figure. Now, looking at the red shows the flow directions, and the triangles themselves indicate where the flood limit is identified. So the flood limit again delineates between bidirectional estuarine flows. So we have bidirectional flow here in the seaward reach and unidirectional flow seaward that's tidally influenced in this landward area. Now we can see a general shift in a seaward direction as discharge increases. So I decided to use some conservation of energy and some idealizing of the geometry of the system, assuming it's in morphodynamic equilibrium or near equilibrium, and solved for an equation to identify where the flood limit is located. And this equation, or the solution, actually does a very good job, I found, of capturing where the flood limit is at. So now in this red fill, we have the estuary, where we have bidirectional flow. For comparison, I have the median discharge here at which is about 1,000 cubic meters per second. And this then indicates that roughly half the time we have bidirectional estuarine flow that reaches up into the middle and upper delta regions. And then higher discharge events push the seaward, and the bidirectional flow is then limited even to just the lower bay at high discharge. Now, next, I want to bring in the tidal amplitudes. So these are shown with circles capturing the water levels, and the squares, the velocity. The fill shows peak amplitudes, and the hollow ones show the limit, or the tidal limit. As we see, this is also changing with the discharge, moving in a seaward direction. So using some additional analytical work and combining some new theory from Kastner et al., I've then delineated roughly where we have tidal attenuation from river discharge, where this fill area shows where river currents are strong enough to increase the friction, which then decreases the tidal amplitude. Now, this still does not fully explain why the tides actually amplify in this region down here. So I decided to look at the salt limit, which I have here in the diamonds, and the salt limit roughly follows this blue line. And with the presence of salt here, this then suggests that the primary role of river discharge in these seaward reaches is actually to increase stratification. So this higher stratification reduces friction, which then amplifies the tides. So we can then delineate these dynamics there. Now, I want to just kind of overall point out to you kind of the take-home piece here is that these dynamics themselves with the river discharge shifts the entire estuary and tidal river roughly 180 kilometers longitudinally in the system within a discharge range that happens almost on an annual basis, which is quite a ways and is very dynamic. So to summarize this chapter here, the river flows and the geometry strongly affect the tides, creating a tide-river geomorphic dynamic equilibrium. The river discharge itself has two main effects. One in the seaward reach is to increase stratification, which reduces friction and amplifies the tides. In the landward reaches, the river discharge causes the flow to be faster, which then increases the friction and attenuates the tides. This can then be delineated following analytical work from Kastner et al. And supporting that work. And lastly, we can then also delineate and identify where exactly this change occurs longitudinally along the system using an analytical solution. And this will soon be submitted. So now pulling these pieces together, I just want to end in a brief closing summary here. So along the fluvial-marine transition, we have a variety of long waves, particularly river waves, surge and tide that we looked at today. The river waves are often the largest, but they can be the slowest. The tidal waves can be the smallest, but they can also be the fastest. Surge waves often are in the middle. Now, these dynamics can change dramatically depending on which side of the transition that you're on and some of the overall geometry changes in the system. So then, although these waves may follow linear wave theory generally, each wave can play out differently in terms of the other underlying dynamics in the system. This creates temporal and spatial variability. And then interacting together, these waves are nonlinear and highly dynamic throughout the system. More broadly, the results here suggest that as global warming is causing a global precipitation intensification, this is globally increasing the magnitude and frequency of river flooding. And I'd like to just close here encouraging those of us who work in the fluvial marine transition. We may all have our different focused areas, but if we want to better understand more broadly what is happening in our areas or even across the transition, we really need to broaden out our work to look at the overall dynamics that are happening from traditional rivers all the way to the sea. And so this also needs to be done for global models and to really understand overall processes happening throughout the world. And so this can really only be done if we have more transitional cross-disciplinary, or sorry, more cross-disciplinary work from the oceanography, hydrology, and geology communities working together. So thank you.
Nice job, Steve. So traditionally what we do is we have open questions from the public forum here. And then after which Steve and the committee will go into closed quarters and we'll chat with Steve some more. So I'd like to open this up to anybody who is